Like Ina said, this is part 1 of 2 for Groovy scripting, an introduction to the API for extending IJC. If you attended our previous webinars on the IJC architecture and basic API for that, then you'll be pretty much good to go. We're making some assumptions about this particular portion in that you have attended the developer webinars part 1 and 2, and basically what we're assuming you have is an understanding of DML versus DDL. You understand what a DF entity, field, and data tree are, and what a DF data entity provider and result set are. And also the basic concept of locks and environments that we covered back then. Because I won't be explaining them, we'll just be referring to them as we go through these. So we're going to be looking at some actual code snippets as we go through and discuss the API and how this is used within Instant JChem. And some of these things that you might be using these particular portions for are doing custom imports into IJC or custom exports for file writing. We'll also be looking at how one does database data modifications, such as inserting or altering data. We'll be looking at how to calculate chemical properties beyond those that automatically come with the GUI, such as using our chemical terms library. And we'll also look at how to modify the structure of an entity, such as creating a new entity or adding a new field itself. So this whole webinar series on extending IJC is based on Groovy scripting. And there's 2 real ways to extend Instant JChem. One of them is via Java extension modules. And these are a much larger and more complicated way to extend IJC. However, it does give you a lot more complicated or involved options through the Java API. And the downside of these, however, is that, again, they are complex, so they are difficult to deploy, and you have to worry about versioning because they are a plugin. However, scripting, which is the approach we're going to be taking for extending Instant JChem, is done all within IJC, and it is part of the data itself. The scripts reside in the database, so you don't have to worry about versioning. They're always with the data and not the version of the thick client. We are using Groovy, which has a full access to the APIs, and they're simpler. They're a lot simpler to write and deploy. The downside is that they are simpler to write, so there's not as much power behind them as a plugin, and there's fewer integration options. However, that being said, we definitely prefer the scripting route for extending IJC and customizing it for your own needs. So with that, there are a couple different kinds of scripts that we'll be talking about, and each has their own caveats based on their type and their location. Schema scripts themselves are used generally for modifying database structure and have specific calls based on where they are. A data tree just has a script attached to the data tree and is usually used for actually manipulating the data, altering the structure, or doing customized imports and exports. And those are the 2 that we'll be covering in this particular webinar series. The other ones, form buttons, event hooks, and calculated fields, we'll be looking at in part 2. So we can kind of put those to the side for now and just focus on the basic scripting and schema scripts and data tree scripts. So why did we go with Groovy when the scripting was designed for Instant JChem in the first place? Well, Groovy is a dynamic programming language which is built on top of Java. It's a lot easier to understand than Java. And it is, let's see what else is there. It's compiled to the Java bytecode. You can access all of the JVM libraries. Groovy scripting within IJC also has access to the public and private classes of the API, which Java does not. So we went with Groovy due to its simplicity and its power. I mentioned before that scripting has its limitations. So some of these are that it needs to be a single file. If you have complicated operations that need to be divvied out into externally accessed libraries, the IJC editor, for anyone who's messed with it before, can see that it is pretty useless, which is something that we're improving on. And it has no debugging or support or unit testing. However, it's very easy to work on your own scripts in an external IDE using imported libraries, and then you can get to your versioning and your autocomplete and all those other fantastic functions that you miss sorely in the IJC editor. I mentioned that for more complicated options or code that is reused often, you want to push that into an external library. And what you can do is you can functionally create a jar that is a wrapper, a thin wrapper around an IJC script that you can access from within the code itself. The benefit of this is, as with any IDE or Java file, you can deal with code completion. There is versioning control, and you also have unit testing. So if you were going to do this from within an instant JChem, effectively what you would do is take your code and build it into a jar file that you would then have deployed upon an internal or external Maven or Ivy repository. And then using Groovy's grapes, you can then simply grab that jar from within your own script, and thus you've accessed your own customized code. Or if you have code or programs that are used often, this is a lot easier than just repeating big chunks of code. And we will talk about this a little bit more in detail when we get there. So if we were going to look at the difference between two major types of scripting, we're going to be talking about schema and data tree scripts today. And these are defined as part of the schema or the data tree themselves. So these scripts are stored as XML within your IJC custom items tables. If you remember, when you set up instant JChem, it creates a number of these IJC underscore whatever tables within the database schema itself. So the custom items contains the XML for the scripts themselves. And as we talked about in the previous webinar series, these are still user-owned, which means you have ownership and sharing options. However, when we deal with button scripting, the button script is stored within the form itself. So the user shared form basically contains the script. However, this still has the same sharing options. Traditionally, you've got the public, private, and shared setting within Instant JChem for sharing of scripts or forms. And in Instant JChem 5.12, we have a lot more strict control of the sharing of these user-owned items. For example, this one is showing how we can partition out particular privileges to roles. So this all applies to scripts as well as forms. So before we start looking at the actual API and examples, I just want to point out a few best practices that we encourage when using the Groovy scripting with an IJC. The first one is to avoid script binding, which we'll talk about after this. The other one is the others are standard best practices for using object-oriented language code, such as structure your code using methods and classes, put your configuration parameters into a single hard-coded section near the top of the script, and any reusable code, especially larger chunks of reusable code, bundle them up in external libraries for repeat and easier access. Now, script binding is something that is specialized to Groovy and a little bit different than Java, especially when we're dealing with Groovy-specific closures. So as an example here, we have three different variables. The first one, in which we just say var1 equals variable1, this is now bound. Bound to the global scope. This is the script binding. So in theory, for the most part, var1 is globally accessible. However, you don't want to bind many variables to the entire global script because it gets rather messy. So the best practice is to keep the variable within the local scope that it's needed of. So what we do this via the def function. So here we've defined variable2 as var2. If you notice, we haven't actually defined the type of variable, and this means it's flexible. So the type will be determined at runtime and can be altered throughout the script. However, if it will forevermore be a particular type of variable, then you can define the strict type, and this avoids the whole runtime determination point of using a flexible type variable. So here we've just said string var3, and by determining the strict type, you are still looking at the local scope. So let's look at a couple examples of how this might function in the real world. If we take our three variable types again, vars 1, 2, and 3, and we were going to make a method called writeMessage1. And here we've put it within a closure, and we simply say, and we call it with writeMessage1. This if we run it, will work just fine, and it'll spit back out message 1 and variable 1. And this is because var1 is in the script binding. It's globally accessible everywhere, so it can be passed in. However, if we were going to make a class that had write message 2, and it's attempting to call var2, which was defined in a local scope elsewhere, so we tried to call write message 2, this is not going to work. And that's because var2 has a local scope elsewhere via the def function. So the methods defined elsewhere are not part of that particular scope. The way around this, because we don't want to do global script binding, is to simply pass in the parameters as options for this particular method. So in this example, we're going to change write message to pass in a parameter, this time called MSG. So if we then try to write message 2 with var2 passed in, because this is now part of the top level scope, this will work fine, and it will pop you back out message 2 param variable 2. Now, closures are something that are particular to Groovy and pretty powerful, and these are functionally just anonymous chunks of code that can take an argument, return a value, and use variables declared in the surrounding scope. So functionally, a closure has access to the global scope. And there's also benefits here that you'll pick up along the way, such as several implicit variables that have a special meaning. For example, if you have a closure with a single argument, you can omit the parameter definition and just use it. And I'll show you an example of that in a little bit. But if you are into the coding facets, this is definitely worth looking up, as the power of closures can be extended in a number of ways through Groovy. So if we were going to define closure 1 and closure 2, and my apologies, that's not supposed to be a space there, and then we attempted to call closure 1 and closure 2, both of these will work. Now if we had just made a method that had var2 in the previous section, you'll see that it didn't work. However, because this is a closure, in the code block, it has the scope of the entire script. And in this one it works just fine because var1 was always in the script binding anyway. So now let's make a class, and within this class we're going to do a private string variable, and private declarations are okay within a class, and this is something else that is a lot more of a complicated I guess code philosophy that would be worth looking into if you cared. But we also have here, we're going to make 2 methods, write message and write message 2. Now write message itself will fail because a class does not have access to anything, even the script binding. So once you define a class, you lose all your access to the global script binding here, even if you're calling a closure. However, write message 2, if we're passing in the variable, it will work fine because we've passed the variable into the method when we've called it. For example, up here, if we're going to now create a new object with write message, this is not going to work because, again, no access to the script binding within the class itself. However, once we pass the variable in, var1, this will work just fine. Won't work. Okay, so with those basic ideas under our belt, let's go and actually look at some API and some actual code. So Mollmporter is it's a class of methods that are used for importing molecules into IJC, basically. When we look at these API, or when we're talking about particular classes and methods, up at the top I'll usually put where it resides in the API itself. In Instant JChem, if you're using a particular class or a method, you have to manually import it near the top of the script. This is not unusual for anyone who's used to development in Java or Groovy, but we'll be putting it up here for future reference, especially if you want to go back and look at the API itself. So Mollmporter allows you to import structures from either a structure file, such as an SDF or an RDF, or a URL or a particular path. You can also import molecules from a source text, such as the pre-read contents of a structure file or a string that's passed in from another source. For this example here, we're just going to import a smile string and create a molecule object. Now, a molecule, we'll talk about in a second, but the fundamental principle is that the molecule is the object container for the structure. Whenever we're doing any chemistry with a particular chemical structure, it is a molecule object. So for this particular example, We're putting everything in a try-catch block because if our code bombs out, we don't want IGC to lock up. So even if I don't show you code within a try block, it's always a good idea to put any of your functional code within a particular try block. So here, we're going to create a new molecule object, and we're going to use Mollmporter and the method import mol just to bring in a smile string. At that point, then we'll go off and do something with our molecule, because now we have a molecule object that is understood by IGC and the code to be of this particular smile string. This is also what we would use to input structures from a file while looping through it. So this example is going to show us how to loop through a file while reading our molecule. Again, we're going to set up our Mollmporter here as our particular file and options. Again, this is worth looking at the API if you'd like to see what kind of file you can import or what the options are. So now that we've created a new Mollmporter instance of the file that we referenced, we're also going to create a new empty molecule object. So at this point, we want to loop through the file. So we just have a very simple while loop. It says while we can read through our file and read in a mole of molecule, then we're going to often do something with a mole. And that will just loop through and allow you for each molecule to do something with it. So molecule itself, there's a bit of a tricky concept here that you may run into a lot, and that's a molecule versus a Marvin structure. So molecule is the ChemAxon molecule class that actually contains the chemical structure that we can do chemistry to, such as adding groups or adding bonds and the like. Molecule inherits from a superclass of molecule graph, so you can also have S groups or deal with Cartesian coordinates within that particular molecule. Now, molecule is effectively handled as what we call the native format, and the native format is how it's actually stored in a database or in the file, such as a smile string or the PDB format, or how is it stored in the SD file. Because when you are dealing with instant JChem has a wrapper called a Marvin structure. Molecules coming out of instant JChem tables are going to be as a Marvin structure, which is just a handler for the molecule itself. Therefore, if we want to use any of the chemical structures out of an instant JChem table, we have to effectively convert a Marvin structure back to a molecule object. And we do this by getting the native structure. And the native structure is, again, basically something that a molecule can understand: smiles, PDF, SDF, etc. Grabbing is another concept that's important for Mollmporter. Whenever you bring in a file, whenever you bring in a chemical structure, from a file or a table or whatever, it is converted to a molecule. Now, if you, let's say you wanted to do something with a smile string, and you imported a smile string into a script, well, now it's a molecule class, and then you then convert it back to a smile string again. We've just gone through 2 conversions, and most of the time that would be fine. But once in a while, you might run into some problems. So what you functionally want to do in this case is pass in your smile string as a string itself. You don't want to do any of the molecule conversions. And this is what grabbing is. It grabs the original text from the file and avoids the conversions to a molecule itself. So if we're going to put this together in a little snippet down here, we're going to first import our Mollmporter and our molecule class for utility. We're again going to set up our importing of a file, and now we're going to enable grabbing. So our Mollmporter can now use the grabbing feature to grab the actual native format from the file itself, as opposed to forcing everything to be converted to a molecule object. So here we go down here. While we're going to loop through our file, I'm going to create a mol string, which is just going to be my smile string, so string, mol string. And from my importer, I'm going to do grabbed molecule string. I still have my molecule object that I'm reading in, but now I also have mol string, which is just my straight up smile string that I pulled from my file. So at this point, I could continue on with the script and go off and do something with either my molecule object or my smile string. Fetching data from within instant JChem tables is a little bit more complicated. If you think back to our developer series when we talked about the DF result set and vertex states, hopefully that you'll recall that the vertex state was effectively a snapshot of the current data. So when we want to go and pull data from an IJC table, we're going to effectively pull it from the vertex state itself. So if we're looking at pulling a row of data, and we'll look at this in a little bit more detail in the next slide, we are going to effectively use the getDataConvenience method on the vertex state. And the vertex state is simply the access to the data itself. And in this case, we're just simply saying on this particular row ID, get this row of data. And what this looks like is an array of maps. So the first thing I want to show you before we do this is how fields are defined, because we're going to need this to pull the row data in a second. So if I'm going to define my field, let's say I have a structure table, and I obviously then have a structure field. Well, what I want to do is I need to specify where this field is in order to pull the data from it. So I'm going to take all the fields from my entity, and I want to go off and find the field where the name is structure. And then I'm going to print line structure field is this. So we're going to echo it out. And what we get here is basically an array of properties for this particular field. Again, name is structure. That's how we called it. You could also do this on the ID, but obviously that's a little bit more complicated. The name is often a way to go. And if you see, for this particular one, the type here is a IJC implementation of a standard database field. So DB JChem structure implementation, which is not terribly important, but it helps in troubleshooting. So here's our row data, our call command again. So first I'm going to define what my row data is, because you pull an entire row of data effectively at once when you're pulling data from instant JChem. And this is just a map of maps, which are keyed by the ID of row and then the field. So if we echo out our row data here, it's going to show us that our for ID 10, row ID 10, this field has this property. This field has this property, this field has this property, and so on and so forth. And what we're entering, what we then start to enter is a very long and complicated structure file, which we don't need to show because that would take pages and pages of a Marvin structure MRV here. But if we only wanted to pull the structure itself, at this point, we just use the key and value call again. So on my my structure is going to be from this row data, just get the value from this particular key, get the value for structure field.id. So if you see our structure field.id as defined, it's going to be this long string here, and then it's just going to pull the value for that particular key. And down here, if I want to make a molecule of it so I can do some chemistry, I'm just going to get the native version, native format from my Marvin structure, which is just a wrapper for the molecule. So now I have my mole, and I can go and do some nifty stuff with it, such as look at the properties. So properties for molecules are handled either via an mprop handler or straight as an attached molecule property. And this is based on if you are getting or setting the molecule properties. So for this example, I'm getting a particular property, which are all attached to the molecule objects as keyed and values. So if I wanted to pull the property for name, I'm going to take my property handler class, and I want to convert to string from my properties the value for name. So pull me the value for name as the key item from my properties handler, and that becomes molName. Setting the properties is a little bit easier because we're going through the molecule class. And we do have a deprecated method for getting properties via molecule, but we're encouraging people to go through the mProperty handler class because there's a lot more things you can do via the mProperty handler class. If this is of concern, please go and check the API. There's actually a decent discussion on that page about using the mprop handler as opposed to just the get and set properties here. But the set property component for the molecule object just looks at the key and value again based on the string. So if I wanted to set the property for a particular molecule of name, then I just put the name and value. For example, let's say we're going to loop through our file again And while we're waiting for each molecule, I'm going to grab my molecule string again. This is grabbing the actual string from the file and not converting it to a molecule. And then let's say I'm going to set the mole name variable and the mole pKa variables by reading in from the properties the property that has the key of name and the key of pKa. Now I'm just going to echo it out. Molecule is whatever name with a pKa of whatever. At that point, you can then do things with these particular values, inserting or editing the data, and we'll be looking at this exact little snippet in an actual piece of code in a minute. MolExporter is functionally just the opposite of Mollmporter. It's for writing out files. In this case, you would just have to import the MolExporter class, and it supports the same file formats as Mollmporter. You can write out a mol file, an SDF, a SMILES. You can make images through MolExporter, PNGs and JPEGs. There's a wide variety of formats that you can write out with MolExporter. So here we have a snippet of data that is going to write out a molecule to a file. So the first thing we want to do is create our exporter instance. So we're going to say new exporter, and I'm going to give it a file name, and it's of type SDF. So now I have an exporter object that will write to an SDF file of whatever value name I've given it here in the file option. So now that I have defined that, I want to go and get a molecule from an IJC table. So I'm going to def my data access as my get data method from my root vertex state for this particular row of ID. Now, my get mol is going to be the molecule that comes out of the structure field for this particular row of data. So get mol is now my Marvin structure, but I can't do much with the Marvin structure. So I need to get the native, which is the molecule object again. And I'm doing this all in one big call here, where I'm taking my get mol, and I'm going to do something a little more complicated, but is also considered best practices. I'm going to not only get the native molecule, I'm going to clone it. The best practice idea here is that you're not making any changes, or you're not dealing with the original molecule itself. You're simply making a copy, doing whatever it is you need to do with it, and then using that. In the case of interrupt or problematic code or anything, it's just a safety precaution. On the off chance that there is a null value here, I've put in the safety switch. So the safety operator will return a null instead of throwing a null point exception if there happens to be no molecule. And of course, if you have a null molecule later down the line, you'll get a complaint, oh, I don't have a molecule, but it won't throw an NPE at this point. So now I have expmol, which is a molecule object, and it's not the original, it's a copy. So at this point, I can clear the properties. Then I can set this property of whatever my new name is. So the property for name is the new name that I'm giving it. And now I'm going to write this out to my file. Exporter, write, molecule. Very simple. And then this will loop through, and once I'm done, well, if I have a loop up here, and then when I'm done with my try block, I will flush and close the exporter just so the file is closed correctly. The other thing that we're going to want to be doing is editing data, which will be inserting or updating. So the first one we're going to do is looking at inserting data. Now, if you remember, editing the data itself is all done through DML, which enters via the actual DDL, which is the architectural structure components of the API at the schema data provider level. And thus, we're going to be using our entity data provider, a DF entity data provider. So really quickly, I want to pop over to some of the actual API from data entity provider and just point out that because this is the entity, the data access point, this is where you can do a number of things to the actual data, such as deleting IDs or getting a row count or inserting data or querying for IDs. When we talk about substructure searching or generating queries themselves, this will be where we're doing it through. It's the entity data provider. So if we go back here, when we're altering the data, obviously you're going to want to lock up the table or the schema wherever you're changing the data, because you don't want somebody else trying to alter the data at the same time you are. we'll call, and it inserts a row, which is just a map of values, into a table. Because IJC has an auto ID creation, we don't have to worry about this. We just simply insert the new values. It will give it a ID and automatically handle it. So the converse, though, is that updating existing data is just a little bit more complicated because we have to effectively identify the ID that we want to update and then identify the specific fields that we want to update while leaving the other ones unchanged. But first, let's look at inserting new row of data. So there's a couple steps here that you're going to need for each altercation of the data itself. The first one is that we have to define our entity. Let's say it's our structure table. So let's get a root or vertex. Let's say it's the top of a data tree. If we had a molecules table at the top of our data tree, then our entity is just going to be the root vertex entity for our data tree. Now, EDP, this is standard nomenclature. You don't have to follow it, but it's considered best practices to do so. EDP is our entity data provider for this particular entity itself. So we're going to indicate that by taking our data, getting our data provider, which is the top level of the DDL, and that's where we enter with the DML for get entity data provider for this particular entity that we've just indicated. So now we have an entity data provider and the entity itself that we can reference to these variables. So now we're going to create a lock. And we looked at this in a little bit in more detail in the previous webinar, so I'll just gloss over it. And that we're going to create a lock for this entity data provider, and then we're going to create a read-write environment that we're just going to label inserting, because that's all we're doing is inserting a row of data. So down here in our try finally block, we're going to build up a map of values that we want to insert. In this case, it's based on the key and value, but it's always based on the key and value for the field and then the value that you want to insert. So for example, we have our structure field.id. Again, we're referring to the field based on the ID, the individual ID. And then we're going to use MolString, which is just going to be our smile string that we pulled previously. Now, when we insert this, edp.insert, we're going to insert our values. This is a sorting option, I believe, and then we indicate our environment, which is just a read-write environment that we've created. Now, because IJC will deal with Marvin structures, it will automatically wrap that smile string and convert it to a Marvin structure. We don't have to worry about conversions whatsoever. When we insert data into a JChem, it understands smile strings or molecule objects, and it will wrap it up into a Marvin structure itself. So at the end of our try finally block, we're going to release our lock, because now somebody else could lock up that table or use the data. And we're going to just close our environment and close out the feedback. And we talked about this previously as well. Updating data just requires a few more steps. So again, we're going to define our entity data provider, our lock, and our environment. Now let's say we want to update a structure. So again, we're going to indicate our structure field and with our new structure string, but we have to tell it which ID, which row are we updating via this mechanism. So we're going to pretend that we've already determined which ID it is. We fetched the ID by matching to a query, or we've manually indicated it, some mechanism. So we're going to build what's called a df update description, and this will simply create a update description object for this particular referenced entity on this particular ID with this map of values. And this could be several fields that we're updating at once, but we're just passing in this particular map. The submitting list has to come in a collections value, and that's how the API simply understands it. So we're just going to pass our update description object into our list creator here. And now we just take our entity data provider, use the update method on our submit list. This is just the ability to undo the update. I usually leave it off simply because at this point I'm pretty sure I want to update that row. And here is my environment again, and the same mechanism. Release our lock, close our environment, and we've updated our row of information. So let's look at a simple script, the fully functional script. And this one I just called file loader, and in a normal interactive script training session, we would be looking at this hands-on with some tutorials. which we will do partially in the UGM or on-site trainings. But for now, for time's sake, we're just going to walk through this a little bit and look at the practical output. So this little script will read through a hard-coded SD file, echo out some information, and load molecules into a currently empty table. So after we import Mollmporter and our molecule classes, we're going to define a few necessary variables. Here I've simply hard-coded the location of an SD file, and effectively it's just referenced as file. Beyond that, we're going to define some necessary variables that we've already seen, our entity and our entity data provider, as well as some relevant fields. Here's our structure field, here's our name field, and we have a field called pKa. For this particular output, I'm going to print these three variables off just to have a look at. But again, this is not necessary in the real world. Now we're going to set up our Mollmporter for reading the file. So we create our new object for Mollmporter, and it is going to import from this reference file. I do want grabbing, and I'm going to create a molecule from this importer object itself. So again, because we're inserting data, we're going to lock it and create a read-write environment. And now in our try block, we're going to loop through the file, or looping through the importer. So while I can read something from the importer, my molecule, I want to get the property from the molecule for name. I want to get the pKa property from the molecule, and I'm just going to echo it out. And then I'm going to insert all three values. We've also here got our classic grabbed molecule string. So I'm going to build up my map. So I'm going to set for the values map with the key of structure field. It's going to be a mol string for the name, mol name, and for the pKa field, pKa. At that point, I want to just insert my array, my map of values into my entity data provider, and then loop again for the next thread. And then when we're all done, again, we're going to release our lock and finish our environment and our feedback. And when we actually run this little script, the output looks like this. Here's those three fields that we echoed out for giggles. See, name structure, name equals pKa, with our field types. And then we also had it echoing out the name of the molecule and the pKa as we inserted each row. So as it cycles through the file, it's just simply set that out, the name and the pKa. And on our IGC side, we have inserted structure. Again, it automatically wrapped it and treats it as a molecular structure. Here's our name and our pKa and the mole weight formula, which are just always added as automatic calculators for a structure table. So that's a very basic loading mechanism that can then be highly customized and tweaked. But let's look at chemical terms real quick. And if you've worked with IJC before within the GUI, you'll know that there are several chemical terms that you can build up in like a calculated field, but accessing them through a script requires a little bit more involvement. So this is the access to the non-API chemistry functions. If we were to look at the actual chemical terms library, and I'm not going to scroll through this because this thing is monstrous, just looking at the content, you can see we have a wide variety of functions for calculations all over the board, from naming and IUPAC handling to similarity calculations and all kinds of properties, surface properties, and the like. This is available online to check out if you're interested, and there is a slew of functions that you can then call via the chemical terms API. So if we were going to use this in the scripting facet, there's a couple components that we need. One is a ChemJep, which is our expression parser and evaluator. However, we also need an evaluator object, and this is the thing that actually directly interacts with the chemical terms library. So this will create the ChemJep object and then interact with the library functions itself. And then you also need the mole context, which is the ability to take our molecule for the evaluation context and deal with the fingerprint analysis as well. And this is just a standard little snippet that you'll use if you're accessing chemical terms data. So let's look at our example here in which we're just going to create our molecule And at this point, I just want to create it from a smile string. So I'm going to take my little smile string and import it into a molecule object mol. Now I'm going to create a new evaluator. And I'm also going to create a new ChemJep. But the ChemJep is just a compilation from our evaluator object of a particular string. In this case, it's pKa, the first acidic pKa. And this is straight, this component here is straight from the chemical terms library. So when you're looking through the library and you want to calculate a particular chemical term, this is already referenced for you. And you just simply put this in the brackets, and it will be understood and compiled by the evaluator. So our mole context, what are we operating on? Well, we're going to set our molecule that we're operating on as our mole. So for our mole context, we're just going to set it as the molecule here, pass that in. Well, now we're going to effectively evaluate it. So we're defining our result as our evaluation of our molecule context for the ChemJep itself, which is the evaluation parser. So result will now be the automatically determined variable of what the first acidic pKa is. Now this is something to pay attention to if you're just using def, in that it will determine the variable type, because def is a flexible variable type, on what comes back from the evaluation of that particular chemical term itself. And sometimes you may have interactions with float versus decimal, or some other kind of numbering scheme. If you run into problems with chemical terms, this is one thing to look at, is what the variables are, what the variable type is determined as after the ChemJep is evaluated. So a couple other things we're going to look at quickly to round this out. If we go back to the DDL, which is our structure, our actual structure and architecture language for Instant JChem, there's a couple things that we're going to need to do, such as creating a new entity. So because we're going to add in, creating a new entity alters the schema architecture, we're going to do this at the schema level. Now, fortunately, there are some helper methods for standard JChem structure creation. For entities that are very common to create, we have created some helper methods, which are just super easy to use and actually very helpful as compared to creating this manually, which we'll demonstrate in just a second. So for our little snippet here, we're again going to set our lock in our environment. And this time we're locking the whole schema because we're creating a new entity. And down in our try finally block, we're simply going to say our new structure entity is a create JChem entity at the schema level, call it structures in this environment. Now we're going to create a standard entity at the schema, call it data in this environment. So we've got create standard entity and create JChem entity. Pretty straightforward. Then release the lock. However, the thing to pay attention to here is that these helper methods are not stored in df entity. It's stored in df entities, which is a bit of a new class, but it's still DDL. So that's something to pay attention to when you're looking for helper methods. And the same thing holds true for creating a new field. Fields belong to the entity parent. So you're going to use a helper method that comes from the entity itself. And here we're going to, again, lock up our entity, create our environment, and then call our helper method. So let's say we want to make a new text field. So we'd have our text field as create text field. And the options there are where, entity, what's the field name, text field name, and then what's the column name. And this is just what it's going to be referenced as in the database itself. And then release our lock and finish our environment. Again, the helper methods are not in df field, they are in df fields. So the reason that we've created these new helpers is that creating new fields without them is very, very complicated. And fortunately, you won't have to deal with this much unless you are wanting to create specialized custom fields. This particular code snippet is for creating a field of the blob type. If there is no helper method for that currently, then you have to go through this song and dance in which you're pulling out field capabilities and classes and looking for combinations of class types which are buried within capability objects. Point being, it's messy. And if you need to do this, if you need to create fields that are, or entities for which there are no helper methods, then we encourage you to get in contact with one of us. That would probably be the easiest route. We do have this particular snippet available online, but beyond this, it does get a little complex. So we're happy to go over this particular code with anyone who is curious to that level. But for now, we'll just gloss over it and say that helper methods are your friend. So that wraps up part 1 of our Groovy scripting webinar. Part 2, we're going to look at some more advanced features such as structure searching. We'll be looking at building user interfaces with Swing. We'll be looking at how to standardize libraries, and we'll also be looking at external library access that we mentioned previously with Maven and Grapes, and how to call those external services. We'll look at button scripting and how that differentiates from data tree or schema scripting. And we'll also look at event hooks, which is a reasonably new feature in which you can attach a script to a particular event on a form, such as double-clicking a cell or right-clicking. So that wraps us up for part 1. If you have any questions, please let us know, or please email us, and I will turn it back over to Janosch. Thank you.